In this video, we will develop and use quadratic formula. Quadratic formula, which is displayed here, arises from solving the standard form of quadratic equation, ax squared plus bx plus c equals 0, in the process of completing the square. So let's develop quadratic formula. We're going to follow the steps of completing the square that we talked about in the previous video when solving this general quadratic equation. So what was the first step? We wanted to have a leading coefficient equal to 1. Therefore, we need to divide the whole equation by a. Then we end up with x squared plus b over a x plus c over a equals 0. The next step would be to look at these first two terms and complete the square. So we prepare the bracket, square it. What's in the bracket? X, the sign that we see, so it's plus, and half of this middle coefficient. So half of b over a is b over 2a. To take half of a fraction, it's enough to place 2 in the denominator of this fraction. And then, since this perfect square is larger than the first two terms, we need to subtract the third term of the perfect square formula, which is perfect square of the number that we took in a bracket. So we are subtracting b squared over 4a squared. Now we may want to either copy the rest, plus c over a, or move this fraction to the other side. Let's move it to the other side. It becomes negative c over a. In the next step, we want to leave this unknown square on one side of the equation and bring all numerical expressions to the other side. So this expression becomes plus b squared over 4a squared. Now, since we predict that we need to add these two fractions, let's write this negative c over a with the denominator 4a squared. So what do we have to do with this fraction to get denominator 4a squared? We multiply top and the bottom by 4a. So in the numerator 4a as well. Therefore, overall we have negative 4ac over 4a squared. So now we can rewrite this equation using one division bar. We have x plus b over 2a squared equals b squared minus 4ac over 4a squared. Well, as you see, we've got already one part of our quadratic formula, b squared minus 4ac. That's a very important expression. It's actually called discriminant. Okay, what's the next step? Now we need to take square root on both sides of the equation. So on the left, we have x plus b over 2a. And on the right, remember to write plus or minus. This is because we're not using absolute value on the left. And then split the root over the numerator, root of b squared minus 4ac. Everything over square root of 4a squared is 2a. Why did I write just a, not absolute value of a? That's what square root of a squared is supposed to be, isn't it? However, notice that even if the sign of a would be negative, this negative sign could be moved to the numerator, and the only thing that will be affected by it is these two signs. They will reverse, it will be minus plus. But overall we'll get the same two possibilities, plus or minus. So there is no need to use this absolute value here because the result is exactly the same. And finally, we can solve for x by moving this fraction to the other side. Notice that we have exactly the same denominators, so we can actually place everything under common denominator 2a. And therefore b becomes negative b, and then we have plus minus square root of b squared minus 4ac, our discriminant. So here it is. That's how we develop quadratic formula. Observe that this formula tells us about solutions of a quadratic equation. The number of solutions of a quadratic equation depends on this expression, b squared minus 4ac, which is called discriminant, often denoted by the Greek letter delta. So delta, the discriminant, equals b squared minus 4ac. How come the number of solutions depends on the discriminant? Well, because, for example, if this discriminant is 0, this case, then the two possibilities disappear. They are actually the same because we are adding or subtracting 0. So the only root is actually negative b over 2a. X is negative b over 2a in this case. Therefore, we can conclude that if the discriminant is 0, we have exactly one solution, and that's a rational number solution. Sometimes this one solution is called double, just because it comes from both cases, the one with the plus and the one with the minus. It gives the same solution. If the discriminant is bigger than 0, then the root is a positive real number, and therefore our solution is negative b plus minus something over 2a, which means we have two real solutions. And finally, if the discriminant is actually negative, since we are unable to take square root of a negative number, we have no real solutions. No real solutions. Instead, we have two different complex solutions, because square root of a negative number is a complex number. Let's visualize these three cases in the system of coordinates. If the discriminant is bigger than 0, we have two different real solutions. How can we see it? The graph of the quadratic equation is a parabola, so for example, it may look like this. This parabola will cross x-axis in two places. Those are the two real solutions. Obviously, the parabola could be with arms up or arms down, but we still have two real solutions. In the second case, when the discriminant is 0, we have one double real solution. Geometrically, it looks like this. The parabola, the graph of our quadratic equation, is just touching the x-axis in one place. And again, the parabola could go this way, but still we have just one solution, one point that the parabola touches x-axis, while here we had 2 points, right? And finally, if the discriminant is negative, we don't have any real solution. The situation looks like this. In the system of coordinates, our parabola may look like this or like that. It does not touch x-axis at all. One more remark. In terms of discriminant, the quadratic formula takes a little bit shorter form, so maybe it's easier to remember. Negative b plus minus square root of discriminant over 2a. However, we need to remember that discriminant is b squared minus 4ac. So it is important that you memorize the quadratic formula either in this full form or two shorter formulas like this. What else can we state about the roots by looking at the discriminant? Well, if the discriminant is a perfect square number, imagine that we have a perfect square number under the root, the value of the root is a whole number. Therefore, the overall numerator will be actually an integer. So our roots are rational. That really means that we could solve our original equation by factoring. Otherwise, if the radicand, which is discriminant, is not a perfect square, then the radical is irrational and consequently the roots are irrational. Therefore, we can claim that the equation is not solvable by factoring. Then we have to use quadratic formula. Now it's a good place to pause the video and think about it. How could we recover factors of the quadratic trinomial knowing the rational roots of the corresponding quadratic equation? I hope you can answer this question on your own. Let's solve these equations using quadratic formula. And here we have a reminder what the quadratic formula is. So my first advice would be to move everything to one side and arrange in decreasing order of exponents. We need to see what's a, b, and c. Okay, 3p squared plus 8p plus 1 equals 0. If we write it this way, we know that a is 3, b is 8, and c is 1. It's a good idea to list our a, b, c on the side, so it will be easier for us to plug the correct values into the formula. Okay, since we are solving for p, instead of x, we are using p. We can use p with subindex 1 or 2 because we expect two roots, right? Equals negative b, which is negative 8, plus or minus square root of b squared, which is 64, minus from the formula, 4 from the formula, a is 3, and c is 1, so we don't need to write it. Everything over 2 times a, which is 6 altogether. And then simplify. So we have negative 8 plus minus root of 64 minus 12 is 52 over 6. And now let's try to simplify. Can we simplify 52? Well, maybe we can help ourselves with a factor 3 on the side. 52 factors into 2 times 26, which factors into 2 times 13. So we can pull 1 2 out of this pair of 2's. Therefore, we have negative 8 plus minus, pull the 2 out of the root, and under the root we have 13. Everything over 6. And then we need to check if it's possible to simplify this any further. Since in the numerator we have a common factor 2, let's pull it out of the bracket. So in the bracket we have negative 4 plus minus root 13 over 6. And now we are ready to reduce 2 with 6, leaving 3 in the bottom. So the final answer is negative 4 plus minus root 13 over 3. We need to give the final solution in a simplified form. Okay, let's try example B. Again, first we need to rewrite this equation as a quadratic equation in a standard form. So let's release the bracket. We have negative 2t squared, negative 4t, and bring the 3 over, so it's plus 3 equals 0. Since it's nicer to start with a positive coefficient a, let's multiply the whole equation by negative 1. That means change all signs. That looks better, less negatives to work with, less likely to make mistakes, right? And as usual, let's list a, b, and c on the side. Our a is 2, b is 4, and c is negative 3. We need to write the numerical coefficients with their signs. The signs are very important. So the solution t, either 1 or 2, is negative b, so it's negative 4, plus minus square root of b squared, which is 16, minus 4a, which is 2, times c, which is negative 3. Everything over 2 times a, which in this case is 4. And now we need to simplify it. So we have negative 4 plus minus root of 16, and here we have plus 24. So altogether is 40. Everything over 4. Now, 40 can be split into 4 times 10, so we can pull the 2 out of this radical. Therefore, we have negative 4 plus minus 2 root 10, everything over 4. And that equals to, let's factor the 2 out, negative 2 plus minus root 10 inside the bracket over 4. And now we're ready to reduce the 2 with the 4, leaving the 2 in the denominator. So the overall answer is negative 2 plus or minus root 10 divided by 2. Here's our final solution. Most often we'll be expected to give the final answer in an exact form. That means using those roots in simplified form. If someone wonders approximately how much is that, then plug into the calculator and figure it out. We need to enter to the calculator one case at a time. So let's enter the case with the positive sign. Since it's important to keep numerator as a whole, let's place a bracket first, then negative 2, but remember to use the negative sign rather than subtraction sign. So negative 2 plus square root, so second x squared bracket of 10. Close the bracket for the root and close the bracket for the numerator. Now we divide by 2 and enter. So the value of this root is approximately 0.58 hundredths. Now to evaluate the second case with the negative, instead of entering the whole expression again, what we can do is push second enter, which recalls the previous entry, and the only thing that we need to change is this sign. This is just a more effective, time-saving way of entering similar expression to the calculator. And enter. So the other root is approximately negative 2.58. The approximate values can be expected in word problem situation. However, when we solve equation, we want the exact values. Okay, let's try another example. This time our original equation is rational. Well, let's see what will happen when we try to solve it. Remember, to solve a rational equation, we multiply the whole equation by the least common denominator, which in this case is 3y and the bracket y plus 2. So let's do this. When we multiply the first fraction by this LCD, the y will be reduced, so what we end up with is just 3 and the bracket y plus 2, right? Then the second fraction, the y plus 2, the whole bracket will be reduced, therefore we end up with just 3y. And finally, the 3 will be reduced, so we end up with y times the bracket y plus 2. Now let's release all those brackets. We get 3y plus 6 plus another 3y equals y squared plus 2y. Let's move everything to the right, but start writing it from the left. So y squared, and then it's plus 2y, but here we have 6y. When we move the 6y to the right, becomes negative 6y. Negative 6 plus 2 is negative 4y. And finally, bring the 6 over to the right, it's negative 6. Okay, equals 0. So yes, in the end, we have a quadratic equation. We can solve it by using quadratic formula. Therefore, our y, 1 or 2 equals. Let's see clearly our a, b, and c coefficients. So a is 1, b is negative 4, and c is negative 6. Negative b is just 4. Because of the two negatives. Plus minus square root of b squared, so negative 4 squared is positive 16, minus 4 times a, which is 1, times c, which is negative 6. Everything over 2 times a, so it's just 2. We have 4 plus minus. Here we have positive 24 and 16. Oh, that's the same as before, root of 40. Everything over 2. Okay, now we can simplify this root 40 to 2 root 10. So we have 4 plus minus 2 root 10, everything over 2. And finally, we can reduce the 2 by factoring it from the numerator and reducing with the 2 in the denominator. So when we reduce the 2, we end up with just 2 plus minus root 10. So this time, our final answer doesn't even have the denominator. And the last example, we start with a radical equation. How do we solve this equation? Well, we should get rid of the square root. So we're squaring both sides, right? Therefore, we have 4x squared on the left, and here it's 11x plus 3. Let's move everything to one side, equals 0. And as usual, we're going to list our a, b, and c. A is 4, b is negative 11, c is negative 3. Okay, let's start finding our roots. X, 1 or 2 is negative b, so it's 11, plus minus square root of b squared, so it's 121, minus 4 times a, which is 4, and times c, which is negative 3. Here we go. Everything over 2 times a, so 2 times 4 is 8. And simplify. 11 plus minus root of 16 times 3 is 48, so we really have 121 plus 48. That gives us 169. Everything over 8. Well, that's great. 169 is a perfect square number, so we can get rid of this root instantly. It's actually 11 plus or minus 13 over 8, which gives us two roots. One with plus, one with minus. So 11 plus 13 is 24. 24 over 8 is 3. Or 11 minus 13 is negative 2. Negative 2 over 8 is negative 1/4. So we can say our solution x is either 3 or negative 1/4. Notice that in this case our discriminant was a perfect square number. That's why we ended up with nice rational answers. That also tells us that this equation was possible to solve by factoring. Let's see how we could factor this. Let's prepare two brackets. This could be factored into 4x plus 1 and x minus 3. We can check this easily by foiling that yes, that's the same. The last term product is negative 3, the first term product is 4x squared, and the middle term comes from multiplying the inner and outer and adding them up. So it's 1x minus 12x. Yes, it's negative 11x. So yes, we could do it by factoring and we would get those roots instantly, but we wanted to practice using quadratic formula in this example. And one more example. Using the discriminant, tell the number and type of solutions for each equation without actually solving it. So we don't have to worry about solving those equations. We just need to tell how many roots and what kind of roots should we expect. Also, could we determine whether or not the equation can be solved by factoring? So, in order to do that, we need to calculate discriminant for each equation, right? Discriminant delta here is b squared, which is 64, minus 4ac, 4 times 5 times 3. Okay, so here we have 20 times 3 is 60. 64 minus 60 is just 4, so discriminant is positive. Therefore, we have two real solutions. And even more, since discriminant is a perfect square number, we also know that our equation can be solved by factoring. So yes, we can factor. As you see, discriminant gives us a lot of useful information. Let's look at the second example. Our discriminant is b squared, which is 1, minus 4 times a times c. So it's 4 times 1 times 1, right? So it's really negative 3. Since discriminant is negative, we have no real roots. There are two complex roots, but no real roots. The following example, again, let's calculate discriminant b squared, which is 4, minus 4 times a times c. Since these two negatives makes it positive, we have 8 times 3 is 24, plus 4 is 28. So it's a positive discriminant. We have two real roots or solutions, that means the same. However, since the discriminant is not a perfect square, the equation can't be solved by factoring, so no factoring. Let's come back to example B. Obviously, if we don't even have real roots, we definitely can't factor. No factoring. Okay, the final equation, again, discriminant is b squared, which is negative 28 squared, minus 4 times this 4 and times that 49. Okay, let's see how much is that. Negative 28 squared is 784, and then we have 16 times 49, which is also 784. So overall, the discriminant is equal to 0. What does this mean? It means we have one real root. Can the equation be factored or not? Yes, it can, because this one root is actually double root, right? And then you will see in a second why it's called double. So yes, we can factor. And even though the question doesn't ask us about it, well, let's see if we can easily factor this. It looks like the outside terms are perfect square numbers, aren't they? So we could fold it back to 2x for the first term, then minus, and then this is a square of 7, so minus 7, and perfect square equals 0. So as you see, this one root is called double because it comes from two brackets. This is really 2x minus 7 times another 2x minus 7. So each bracket produces one root, particularly 7 halves, right, from both brackets. But since those roots are the same, that's why we have one real root. But it happens twice, two brackets. Okay, so in conclusion, the discriminant is reasonably easy to calculate, and it gives us useful information, firstly about the nature of roots, secondly, whether or not it's worth to use factoring strategy or quadratic formula when solving the given equation.